Good morning, everyone. It's a wonderful conference. I'd like to begin by thanking the organizers, and particularly the tech team, of course, and also Professor Pollack for his kind invitation for me to present today. I'm going to try to be succinct. I tend to be verbose, but I've taken advice on removing slides. In 1996 and 1997, I conducted a series of experiments, acoustics experiments, in the Great Pyramid of Egypt. The 96 experiments were very standard acoustics experiments that any acoustics engineer would recognize, and they were fascinating. And I learned a lot about the ancient Egyptians' knowledge of acoustics and how they had applied it to the king's chamber of the Great Pyramid. But one of the experiments I wanted to conduct was a cymatics experiment, not time to do that in 96. So I went back in 97, gained permission again. And in 1997, the experiments completely changed my life. And the experiment that I needed to conduct concerned cymatics. I had been following the work of Dr. Hans Jenny, who some of you may be familiar with, and I'll mention in this presentation. And he had inspired me to conduct this experiment. Why? Because the sarcophagus, which is this box of rose granite in the king's chamber, is highly resonant. That means that if you strike it with the side of your fist, which I don't think the Antiquities Department like you to do, but if you do that, it rings like a low-pitched bell. And I knew from the experiments that I had conducted in 96 that nearly all of the acoustic energy that you create in the chamber, if you make sound just vocally in the chamber, nearly all of that energy is acoustically coupled and ends up in the sarcophagus. And the sarcophagus being resonant, it absorbs that energy. So I was particularly fascinated to learn about the resonant properties of the sarcophagus, and I decided I would conduct this cymatics experiment. 3 weeks before going out to Egypt, I severely injured my lower back. I was in agony, I was in extreme pain as I entered the pyramid that day, taking probably far too many analgesics to try to mediate the pain. Nothing really touched that pain. I began to set up the experiment. The antiquities inspector helped me to set it up. And within a few minutes, we had the experiment up and running, and it consisted of stretching a membrane across the open top of the sarcophagus, and then a little speaker placed inside the sarcophagus would provide the sound. And the whole idea was to make visible the resonances in that sarcophagus so that I could understand them and study them in great detail back in the lab. What happened was two events that happened that were absolutely extraordinary and life-changing. The first was that within just a few minutes of beginning the experiment, the antiquities inspector and myself began to see ancient Egyptian hieroglyphs appear in the sand that I had sprinkled on the membrane. Ancient Egyptian hieroglyphs, this reminds me so much of the hydroglyphs we were talking about yesterday. But these are literally ancient Egyptian hieroglyphs, or at least that's what they appeared to be. And I was stunned, as was the antiquities inspector, but didn't have much time to really focus on the why of that. How is that even possible? When about 20 minutes into this experiment, I suddenly noticed that I had no pain in my lower back, having had pain for 3 weeks up to this point. So that really got my attention. I thought in the moment, I know what's going on here. I'm excited at seeing these ancient Egyptian hieroglyphs. You know, who wouldn't be under those circumstances? And no doubt there are natural opioids flowing, endorphins flowing in my bloodstream, masking the pain. And so when I get back to the hotel, the pain will come back. The pain never came back. So something really important had happened, and I realized that this could be important for medical science of the future. The other thing, of course, was seeing these ancient Egyptian hieroglyphs. I knew that this had to be something that could be used as a tool, a new tool in science. And that really is the background, how my life changed. So at that time in my life, I was an engineer, and literally I went back to the UK after these experiments, began the process of winding up my business at that time, my acoustics business, and becoming the scientist that I am today. So with that, I'm going to begin my presentation. That image that you see on the screen there now is actually a 3 Hertz delta brain frequency made visible in pure water in the CymaScope instrument. And it has a very interesting shape, but that's not the subject of this talk. First, let's begin with a definition of cymatics. This is my preferred definition. A scientific methodology in which sound interacts with gaseous, particulate, or liquid matter, causing the matter to become organized into form from formlessness. And this word cymatics was coined by Dr. Hans Jenny that I had mentioned, and it derives from the Greek word chyma, meaning wave. Jenny, it seems, was unaware of the scientific term Faraday wave phenomena, after one of my scientific heroes, Michael Faraday. So this term Faraday wave phenomena is very commonly known in science. But the terms cymatic phenomena and Faraday wave phenomena are in fact interchangeable. Also to mention that cymatics is a triadic phenomena. So if you look at that beautiful, what we call a cymaglyph, just another word for sound image on the right there, it looks very permanent, doesn't it? And this is actually a harmonic of the Schumann cavity resonance frequency, 7.83, but a harmonic of that made visible. And I particularly like this cymaglyph because it shows what looks like people holding hands around, well, it could be notionally the earth. I really like the idea of it. But when you look at that, it looks very permanent. Of course, this is actually an illusion. Really, it is not permanent at all. It's a standing wave pattern, a very complex one, that's constantly moving. So the frequency of excitation, in this case, a harmonic of Schumann cavity resonance, generates the dynamic standing wave, which in turn creates this apparent stationary form. So the persistence of vision, our normal vision, sees it literally with normal ocular vision as something permanent. But in reality, cymaglyphs present only this illusion of permanence. And if you study these images, these cymaglyphs, with high-speed photography, for example, or even just different shutter speeds on the camera, you will see different moments of creation within this cymaglyph. Also, the ability of sound to organize matter, scale appears to be entirely irrelevant. On the right there, you see a giant hexagon, a gaseous hexagon, on the north pole of the planet Saturn. It's so large it could swallow 3 Earths. And this is it's literally created by cymatic forces. On the left there, you see a microscopic cymatic pattern, in this case a 10-fold pattern of 105 micrometers diameter. Just to give you a comparison, a macrophage, a large white blood cell, is about 21 micrometers, and I am working up towards imaging literally on the surface of living cells. And this is, one of the facts about cymatics, which is so fascinating, is that when we're immersed in an environment of sound, and of course we're always in sound, there's never a time when we're not in sound, but let's say musical sound, then all those musical sounds are literally imprinting on every cellular membrane in our body. Every cell has a membrane, and the cymatics principle is that whenever you have sound and you have a membrane, there has to be a cymatic pattern. Invisible to the unaided eye, but nevertheless present. You might not know that there are craters on the moon that are hexagonal. These are created by cymatic forces, and there's a paper there showing one of the many potential explanations how this actually occurs physically as an asteroid strikes the moon's surface and the dust is trying to get away but sometimes the speed of the dust trying to get away is impeded, and some of it starts to come back towards the epicenter, and in that moment, geometry is created. Also, there are hexagonal craters on Memes and Ceres. Hexagonal crater on Memes you see there on the left, a moon of Saturn, and a hexagonal crater on Ceres, which is actually a dwarf planet. So come now to Michael Faraday and Hans Jenny, who were both really inspirational for me. Michael Faraday, I have a lovely photo of him in my lab. He looks over my shoulder all the time, making sure that I'm doing my work right. And Hans Jenny, as I mentioned, he inspired me to actually carry out that cymatics experiment in the King's Chamber all those years ago. So I have some quotes here to read from Faraday and from Jenny. So Faraday says, "It's quite comfortable to me to find that experiment need not quail before mathematics, but it's quite competent to rival it in discovery." And I would agree with that entirely. He also said that on putting a candle exactly below the plate and holding a screen of tracing paper an inch above it, the picture given was beautiful. Each heap of sand gave a star of light at its focus, which twinkled. This was exceedingly beautiful and easily rendered visible to a large audience. And there you see him at the Christmas lecture in 1827, the Royal Institution. And then Jenny, this quote from Jenny. He wrote two wonderful books, by the way, mainly pictorial, Cymatics Volume 1 and Volume 2. And in this Cymatics Volume 1, he said this: "Periodicity represents an aspect of the world, and at its first mysteriousness always inspires a feeling of the greatest astonishment. In attempting to observe the phenomena of vibration, one repeatedly feels a spontaneous urge to make the process visible and to provide ocular evidence of their nature. For it is obvious that by virtue of their abundance, clarity, and conscious nature of the information communicated by the eye, our mode of observation must be visual." And of course, this is so true, isn't it? That we understand the world. Most of what we understand about the world comes through our vision. This wonderful lady, Mary D. Waller, has to have special mention, and I'll come back to Mary D. Waller at the end of the presentation. She was an English scientist and professor of physics at Royal Free Hospital Medical School in London, and she made an interesting little discovery one day. She went outside to buy an ice cream from an ice cream seller, and he was using dry ice to keep his ice cream cool. And he happened to touch a little piece of the dry ice on the bicycle bell of this little bicycle that he was carrying his ice cream around with. And it made a singing sound, a ringing sound. And this fascinated Mary D. Waller. And so with that, she began a series of experiments. She was familiar with Ernst Chladni, who had, well, we now know has the honor of being the person who brought this kind of science to light in the first place. A plate that is excited by sound, in this case dry ice, literally placed on the plate, causes the plate to ring like a bell, and then these beautiful patterns emerge from the sound. She created this lovely book, Chladni Figures, A Study in Symmetry. She didn't see it published in her lifetime. It was actually published posthumously. And the reason I'm giving particular mention to Waller is that she's the only person between Chladni, Faraday, Jenny, that actually created a law of cymatics. And this is the law. The normal modal systems of a plate, which has n lines of symmetry, may be divided into classes which are twice as numerous as the number of factors of n. She also said, and a kind of epilogue in her book, it will be good if this account of simple experiment can bring about that the law of symmetry of vibrating systems can be accepted. Isn't it a pity that she wasn't alive to see that come to reality? But it does indeed, as you'll find out. Nothing tends so much to the advancement of knowledge as the application of a new instrument. This is my little plug for the CymaScope Lite instrument, which is actually the latest iteration of the CymaScope instrument, which was inspired by my work in the Great Pyramid all those years ago. Now, this instrument is fully portable. The other CymaScope instruments that we have are all laboratory instruments, calibrated. This instrument also is calibrated. But the difference is, of course, that it's fully portable. It has literal batteries in it. You can take it into the Great Pyramid if you wish to, or sacred burial mounds, or wherever you want, temples, anywhere, basically. And we use electronic filtering, basically, to filter out the natural resonances in the instrument. Same as with the scientific CymaScope. Obviously, all objects in the universe have natural frequencies of vibration. We're not really interested in those resonances in the instrument itself, so we tune them out. We identify them, and then we dial in, literally, a reverse characteristic curve, so that they're literally, we're looking at a flat, pretty flat frequency response. Consequently, it becomes possible to transpose sonic periodicities to water wavelet periodicities. And by the way, water is the best medium for imaging. I had tried many different fluids, as I've mentioned in other presentations at the water conference, but pure water, I'm talking about triple distilled medical grade water, is the very, very best. And here is an A to Z of sciences that can be studied with the CymaScope instrument. There's probably many more, but these are, some of you, I'm sure, will be interested in some of these particular scientific disciplines. And as you see, I've highlighted water science here, which is the talk that we're mentioning today. I'm sure you're all familiar with the fact that all audible sounds are spheroidal or spherical in their space form. And here you see a nice illustration of that with the graph of sound in the middle. But of course, nature does not use graphs. All audible sounds are spherical or spheroidal, let's say, because they're not necessarily perfectly spherical, but they're certainly spheroidal in their space form. And as the sound frequencies increase, so the sound bubble starts to flatten. Ultimately, when you get up to ultrasonic frequencies, which are used in medical science, then the sound becomes like literally like a searchlight beam, very, very narrow. But at kind of all the audible frequencies that humans can hear, it is literally spherical. So it's not a wave, literally. It's a very unusual word to use in relation to what is actually a bubble. Let's examine this beautiful sound bubble which is emerging from this young woman's violin. If we could zoom in somehow to the notional surface of this bubble, this is obviously a frozen moment in time here. If we could zoom into the surface of that bubble and look at an atom or a molecule, the component of the air, we would find that all of the vibrational information in that violin sound, that beautiful violin sound, is contained in that single atom or that single molecule. And the same would be true if we zoomed into anywhere in the interior of that bubble. The same information is contained everywhere within that bubble. And this brings us to the holographic principle. The total information contained in a volume of space corresponds to an equal amount of information contained on the boundary of that space. This is a quote by Zimmerman-Jones. It basically means that every atom and molecule in the sound carries all of the vibrational energy information of the originating sound. And this fact tends to be overlooked when the wavelength of sounds in relation to human tissues is concerned. What is the reason for this extraordinary ability of the cochlea, for example? So an example of the importance of this phenomenon occurs in sonic vibrations that enter the endolymph fluid in the cochlea. The vibrations are conducted to the cilia in the organ of Corti. And therefore, logically, even a single cilia must receive all of the atomic vibrations of the sound, regardless of the sound's notional wavelength or its speed of propagation in endolymph fluid. And by this same logic, the sonic frequencies imparted to atomic and molecular particles in any body of water are holographic, or let's say quasi-holographic in nature. And this brings us to the first postulated law of cymatics. In a dynamic cymatic pattern in water or other fluid media, the frequency information contained in every atom or molecule is identical. And interpreting this importance of this law in terms of our water-rich biology, when sound enters our body, it means that every atom and molecule of the sound carries all of the energy information, thus communicating the sonic information to all aspects of our physiology, even down to the microscopic and submicroscopic scale. And on the right, by the way, you see that beautiful cymaglyph. This is actually the image created by the sound of a bee literally buzzing, and its beautiful sound is made visible in that moment. By the way, bee sounds are very healing. Just to make you feel a little bit comfortable about all of this, here are some simple calculations relating to air and water. The formula for the wavelength of sound, whether in air or water, is given by lambda v over f, where v is the speed of sound and f is its frequency. And then I give a simple example of this, the longest wavelength from a piano note of 27.5 hertz, 12.36 meters long. But sound in water has an approximate speed of 480 meters per second. Therefore, the wavelength of the lowest piano note in open water is about 53.8 meters, more than 4 times its length in air. That's all very commonly known. This is where it gets really interesting. The relationship between wavelength, speed of propagation, and frequency of sound are very well-known aspects of the laws of physics for sound in air or in open water. But in small volumes of fluid, such as in the cochlea, or in our cells, or in the CymaScope instrument's water-filled cuvette, the situation changes. In these examples, sound now enters a bounded area, and the second law of cymatics now operates based on the density of air versus the density of water, and this leads us to the second law of cymatics. A fluid membrane compresses incident sonic periodicities in a ratio governed by the relative densities of the sonic and fluid mediums. And this is due, as I mentioned, to the differential between the density of air and the density of the fluid, in this case, pure water. And there are the actual figures given. And interpreting this, the importance of this law in terms of our biology, it means that all the sounds that enter our body from the environment are compressed by this 829 to 1 ratio when they enter the body's interstitial fluids, the fascia, the organs, and the cells. And on the right there, in this case, this is actually the sound of the sun made visible by the CymaScope instrument. This is from a sound collected by the SOHO spacecraft. And interestingly, some of you will know that there are actually sound bubbles in the sun that are constantly recirculating and rising to the surface. And it's interesting that we see here what appear to be bubbles, or at least these antinodes, around the periphery of this cymaglyph. And here's the experimental proof of the second law of cymatics, what I call holographic encoding principles in bounded water. What you're looking at here are 2 actual photographs. The one on the left doesn't look much like a photo, but it is literally a photo of a 50 millimeter cuvette, which is the instrument, in this case, the low-frequency CymaScope, because we have 3 different models of CymaScope depending upon the frequency range that we're looking at. In this case, 50 millimeters wide, and if you look there, you'll see that every adjacent ring, these are actually reflections literally of a light ring that's above the water. Every adjacent ring is literally describing a half wavelength of the initiating sound. And in those calculations, you can see, again, using the lowest note on a piano, 27.5 hertz, it has a wavelength, the bubble length, of 12,370 millimeters. And if you divide that by 829, you end up with 14.92 millimeters. And if you do the calculations literally on the scale of that 50 millimeter cuvette, you will find exactly that, 14.92 millimeters. This is a kind of, an actual proof. And then going at the other end of the scale, I did this same kind of the same kind of little experiment with a very small cuvette. This is only 4.2 millimeters in diameter. And in this case, I used a particular frequency, 1174 hertz, not for any particular reason, just a high-frequency sound. And you can see very tightly packed concentric rings. By the way, these concentric rings occur just the moment before the cymaglyph blossoms onto the screen in the water. This is called the moment of Faraday instability, and it occurs because of easy water. So what happens is the energy from the epicenter of the water moves out slowly, obviously, to the boundary condition, and there it meets easy water. And this easy water not only has a different refractive index, it also has elasticity properties. So it's absorbing quite a lot of the acoustic energy that's moving out from the epicenter, and initially prevents the reflection of sound, or the prevention of the reflection of these little wavelets, you could say, which are based on sound. But then if you increase the intensity just a little bit more, you overcome the easy water, and the reflection occurs, and then you get the beautiful Faraday wave pattern. Anyway, just enough to say that the same principles that I applied to the photograph on the left, I applied to the right, and again, it comes out exactly right. So this 829 times to 1 seems to be proven. An indication in the nature of the second law of cymatics in action is the cochlea. Again, you might have wondered at some point in your life why it is that a cochlea that's only about 30 millimeters long when it's unwound, how can that little instrument, that little sense really long wavelengths? Well, this is the reason, in my belief. It's because of this 829 to 1 compression. So again, working on that 12.37 meter wavelength, when it's compressed by 829 to 1, it becomes 14.92 millimeters in length, which is only about half the length of the cochlea. Here is the third law of cymatics. Cymatic patterns on a circular membrane represent an encoded model of the sound, since the crests of the waves at the moment before Faraday instability are in phase with the crests of the initiating sound. You can prove this really easily just looking on an oscilloscope instrument at this moment when you're creating this particular cymatic pattern, and then check that literally with the image that you're seeing in reality, literally in the water, and you will find there's exact phase relationship between the oscilloscope instrument and the literal physical manifestation of that in the water. And proof of this law comes from the image of the CymaScope, again, 50 millimeter cuvette, the concentric circles created by standing waves of the 27.5 hertz frequency, created a moment before Faraday instability, are in exact phase with the amplitude crests of the initiating sound, which in this case was a signal derived from an audio oscillator. And interpreting this law in terms of our biology, it means that cymaglyphs are literal geometric models of a therapeutic sound. I'm using that term in particular for a particular reason, and therefore can be used as a therapeutic tool. I mean, obviously they have far more applications than simple therapies, but nevertheless, therapy is one of the areas that I'm particularly interested in, as you will realize when my lower back was healed, apparently healed, within only 20 minutes of making sound in the King's Chamber. And here's just one of many examples of what's termed drishti meditation. Some of you may be familiar with this term. It basically means open-eyed meditation. And here you see a young woman meditating on the sound of the sun, literally. And what happens is that the light in the room is literally incident upon that image, and of course is modulated by the geometries of that image. And then the infrared component, the near-infrared component of that reflected light then enters deeply, penetrates deeply into the tissues of this young woman, and therefore brings with it the healing effects of infrared radiation in a geometric form. And of course, I think you probably all know, it's common knowledge, I think, now, that the cells of our body communicate primarily in the infrared, in the near-infrared spectrum. So literally, this woman is receiving information in the language of her own cells. And then we come to finally the fourth law of cymatics, Normal modes of vibration for a given membrane for a single frequency or multiple frequencies are unlimited in number. The modes are normal in the sense that they can move independently. An excitation of one mode will not cause motion of a different mode. And interpreting this law in terms of our biology, it means that all of our tissues receive a constant stream of ever-changing cymatic patterns when we are immersed in a musical environment, particularly in a musical environment. The idea that a membrane has an unlimited number of normal modes is actually very well known in physics, but the part of this law that's not well known, or not known at all until this moment, is that it also relates that relates to single frequencies, where in fact the law that I'm referring to here, or postulating, means that any frequency, any complex array of frequencies, also can be accommodated by this law, so multiple frequencies. And evidence for this stems from a swept musical chord. In other words, we can put a musical chord into the CymaScope and sweep it up through a range of frequencies, and we will see literally cymaglyphs at every single moment emerging. And this is the proof of this law, basically. And it's a beautiful thing to watch. I should have really brought a video. On the right there, on the right, you see a cymaglyph that was created by 7.97 hertz. We began this experiment with Schumann cavity resonance at 7.83 hertz and literally dialed the oscillator up by 0.01 of a hertz at a time. And not until we got to literally 7.97 did this beautiful cymaglyph blossom onto the screen. So it really is very, very critical indeed, the frequencies of excitation. And finally, just to come back to Mary D. Waller and her law of vibration pattern symmetry in action. So Mary D. Waller's law of vibratory pattern symmetry is seen to play out in this comparison image of the sound of a healthy cell made visible on the left, which is beautifully symmetrical, versus that of the sound of a cancer cell made visible, which is skewed and loosely asymmetrical. And just to mention that I imagine that Mary would be very pleased to know that her proposed law of pattern symmetry has begun to be accepted, at least by me, thanks to this experimental physics. And this, by the way, is this research on the right that you see here, literally comparing the sounds of cancer cells with healthy cells, because all cells emit sound, and cancer cells and healthy cells, of course, emit different frequencies of sound. And the cancer cell, as you see there, creates very kind of skewed and ugly pattern, whereas the healthy cell creates very beautiful patterns. And this was a paper that we published in the Water Journal. Thank you very much for your time.